Welcome to our presentation on the Bitnet Llama project. I am Xu.
And I'm Mabaolu.
And today we will take you through our journey of designing hardware for a highly efficient Bitnet Llama architecture. Let's dive in. Our primary motivation for this project came from a groundbreaking research on 1-bit and 1.58-bit quantization technique for large language models, such as Llama 2. By reducing the precision of weight, we aim to achieve significant improvement in hardware efficiency. The Bitnet Llama architecture builds on a decoder-only transformer structure. We replace the traditional NN.linear blocks with bitlinear blocks. And for 1.58 Bitnet architecture, it does 3 more changes to the model. First, we change layer norm to RMS norm. Second, we change activation function from GLOO to SWIGLOO. And lastly, we add rotary positional embedding to the MHA block. The heart of our design lies in the bitlinear operation. It involves in several key steps. These steps together enable us to represent weight in ternary precision, drastically reducing the memory usage while maintaining the accuracy. For normalization, we use RMS norm, which normalizes each element based on the root mean square of the entire vector. For quantization, we employ absolute max quantization, a technique that can scale the input value and clip them to fit within the targeted range. The key feature of 1.58-bit weight is their ternary representation. This representation allows us to perform matrix multiplication using only additions and subtraction, significantly reducing computational resources. Once the ternary multiplication is complete, we apply dequantization to map the output back to higher precision. Bitnet 1.58 offers substantial memory and energy saving compared to float-point 16 models. For instance, it achieves up to 71 times energy efficiency while maintaining performance parity with float-point 16 model for models larger than 3 billion parameter.
In the paper, it mentions that 1-bit LLMs like Bitnet B1.58 can cut down inference costs while keeping model performance intact. This new way of computing means we need to design new hardware just for 1-bit LLMs. That's why we chose this project, and in our work, we'll be designing this specialized hardware.
Now, let's talk about the challenges we faced during this project. First, we developed integrated stages for RMS norm and absolute max quantization. Combining these operations into simplified and efficient hardware computations, this formed the basis of our proposed bitlinear infrastructure. Second, we address the high computational demands for matrix multiplications by optimizing our PE architecture. Traditional matrix multiplication posed significant challenges. It required excessive computational resources per cycle, had a long critical path, and incurred high hardware costs, making it impractical. By using our PE to perform matrix multiplications, we can significantly lower the critical path, reduce the hardware cost, and split the computation across multiple cycles, ensuring efficiency and feasibility. Lastly, we addressed the PE group management problem. Taking reference from the 7 billion Llama 2 architecture, we set our targeted throughput to approximately 125 tokens per second. We then calculate the overall latency as a function of the number of PE and estimated the throughput accordingly. Initially, our throughput value were too high, so we reduced the number of entries in the pipeline. This adjustment allowed us to set the PE group configuration to 2 for integer 8 calculations and 1 for float-point 8 calculations, achieving an estimated throughput of 115 tokens per second.
Next, I will give a brief overview of the model architecture. The Bitnet Llama architecture consists of 32 sequential layers, each containing 2 primary blocks, attention and MLP. This design uses specialized PEs to efficiently handle bilinear and FPGA. As you can see in the picture, the main difference from the traditional Llama architecture is that NN linear has been replaced with bilinear, while the rest of the structure remains largely unchanged. Now, let's talk about the key part of our design, the hardware design of bilinear. We've broken it down into 4 stages, which I will explain next. This diagram illustrates the pipeline workflow of our bilinear design. First, stage 1, input handling and gamma selection. We start with a 1x1496 FP8 array and split it into 2048 sets, each containing 2 FP8 tokens. Next, we compare these tokens to find the local maximum in each set, then compare it with the maximum stored in the register. If it's larger, we update the register. By the end of this stage, we process all sets and store the final gamma value for the next stage. Next, stage 2, scaling, conversion, and clamping. We scale each FP8 value by multiplying it by 127 and dividing it by gamma, then convert the results into int8 format. After that, we clamp the values to stay within the int8 range of -128 to 127, ensuring clean data for the pipeline. Now, stage 3, PE processing and accumulation. Here, scaled int8 tokens go through processing element PE groups, which handle computations using comparators and adders. Outputs are sent to 1496 accumulators to store intermediate results. This process is cycle efficient. New data is fed into the PEs every 16 cycles, keeping the pipeline active and producing a 1/1496 output in 32 and 7068 cycles. Stage 4. Conversion and final scaling. The accumulated int8 results are converted back to FP8 format. Then, we scale these values by multiplying them with gamma, dividing by 127, and finally multiplying by beta. With these 4 stages, our bilinear design achieves a highly efficient pipeline workflow tailored for its application. This is the hardware design and pipeline workflow of the MHA part. Due to time constraints and the fact that it is not the focus of this project, I will not go into details here. The main point is that, as mentioned earlier, we use only one PE group to perform FP8 multiplication. Now, moving on to the hardware design and pipeline workflow of the MLP part. Similarly, I will just show the hardware design and pipeline workflow without detailed explanation.
In this project, we focus on implementing only the specialized part in hardware, the Bitlinear module. To better suit hardware implementation, we split the workflow into 4 parts. In part 1, we started with the module to find the maximum input value, essential for scaling during the normalization and quantization. In part 2, we combined RMS norm and absolute max quantization into a single module to reduce latency and simplify computations. In part 3, we developed the PE matrix multiplication module, optimized for parallel processing and ternary weight. Lastly, in part 4, a dequantization module was implemented to restore precision for downstream tasks. For simplicity, we will only talk deeply about the implementation of the PE module. First, we create a sub-PE module, which corresponds to a PE array. Then we instantiate multiple sub-PE modules to create 2 PE groups, A1 and A2. By doing this, we could use PEs to perform matrix multiplication. As shown in the waveform, we broadcast the same input to a corresponding weight for 16 cycles, accumulate the result in temporary registers, and output the final matrix multiplication result once the calculation is done. In conclusion, our project demonstrates the potential of low-precision hardware design for large language models. Future work will focus on designing a more efficient storage system and developing a better mechanism for handling the rest of the blocks.